Hello everyone, I'm Hyunjin Choo. I conducted this work during my postdoctoral research after completing my PhD at KAIST, and I'm currently a researcher at HOIs. Today, I present our work titled HyperSearch Prediction of New Hyperedges through Unconstrained yet Efficient Search. Many real-world datasets contain group interactions involving two or more entities. For example, co-authors of a paper, email addresses in an email, tags added to a question, or ingredients in a recipe can all be represented as group interactions. Hypergraphs provide a natural and expressive way to model group interactions. Unlike traditional graphs that connect only two nodes, a hyperedge can connect multiple nodes at once, making it possible to directly represent complex multi-way interactions in a single structure. For example, the three papers shown on the left each have multiple authors, and these groups can be represented as hyperedges. Our task is hyperedge prediction. Given an observed hypergraph, we aim to predict new hyperedges likely to appear in the future. For example, in a co-authorship network, this means predicting future author teams that might write the paper together. Hyperedge prediction has many real-world applications. For example, it enables group recommendation in social networks and can be used for collaboration prediction, such as predicting future co-author teams. It is also useful in drug discovery, where predicting functional groups of genes or proteins can help accelerate biomedical research. One major challenge in hyperedge prediction is the vast search space of possible new hyperedges. Since each hyperedge can involve multiple nodes, the search space grows exponentially with the number of nodes. For example, the DBLP dataset has about 15,000 nodes, and the search space of new hyperedges is larger than 10 to the power of 4,000. Predicting new hyperedges in such a vast space is as challenging as find a needle in a haystack. Many existing methods for hyperedge prediction rely on candidate sets. They typically perform binary classification within these sets, distinguishing only between positive and negative samples. However, how to obtain a promising candidate set with the ground truth is not addressed in these approaches. Other methods avoid candidate sets but depend on structural assumptions. In contrast, our method, HyperSearch, does not require a candidate set. It directly generates a small set of promising candidates from the vast search space in a principled and learnable way. Our goal is to predict new hyperedges from a vast search space. HyperSearch consists of two key components. First, we design a scoring function based on empirical observations, which helps efficiently rank promising hyperedges. Second, we use a rapid top-case search with pruning, which allows us to find the most promising candidates without exploring the entire space. In this work, we aim to predict new hyperedges from a vast search space by scoring each hyperedge candidate based on empirical observations. First, let me introduce two key parents we found in the observed hyperedges. We then use these parents to design our scoring function. Let's first look at the structural parents in hyperedges. We use two sets of hyperedges, ground truth and random. For each set, we split the hyperedges into 20% new and 80% observed and measure the structural overlap between them. We find that the ground truth hyperedges show much higher overlap than the random ones. This indicates that new hyperedges are more likely to substantially overlap with existing ones. Based on this observation, our scoring function prioritizes candidates with higher overlap with observed hyperedges. Next, let's turn to the temporal parents. We also observed a temporal bias in structural overlap. We split the observed hyperedges into 5 equal-sized groups based on timestamp. Then you measure the overlap between each group and the most recent one. The overlap increases as the observed hyperedges become more recent. This suggests that new hyperedges are more likely to resemble recent hyperedges than old ones. Based on this observation, we assign higher weights to more recent hyperedges in our scoring function. Our main idea is to score each new hyperedge based on these observations. That is, we design a scoring scheme that reflects them, and I'll now explain each component in more detail. Let's start with the support concept from frequent item set mining. Given a candidate, it counts the hyperedges that contain all the nodes in the candidate, but the exact covariance can be too strict, so we allow partial covariance through relaxation. We apply 3 relaxation criteria: node, hyperedge, and total, to allow partial covariance. For example, here the candidate has 3 nodes, but no hyperedge contains all 3, so the support is 0. However, if we allow one node to be omitted using a relaxation ratio epsilon, then 3 hyperedges satisfy the condition. The relaxed overlap count is defined as the number of such hyperedges. To reflect how much a candidate overlaps with observed hyperedges, we define an overlap ratio. It measures the ratio of overlapping nodes to the size of the hyperedge. For example, if the candidate overlaps with a hyperedge of size 5 and shares 3 nodes, the overlap ratio is 3/5. This allows us to capture not just the number of overlaps, but also the strengths of each overlap. Finally, to reflect that new hyperedges are more likely to resemble recent ones, we apply a time-based weight to each score. More recent observed hyperedges are assigned larger weight, increasing exponentially with recency. Here is the final scoring function for a hyperedge candidate. For each observed hyperedge that satisfies the relaxation criteria, we multiply the overlap ratio and the time weight. Finally, we tune all hyperparameters, epsilon and tau, using a validation dataset. Next, I'll explain how we efficiently search for promising hyperedge candidates from the vast search space using an effective pruning strategy. Our search strategy efficiently finds high-scoring hyperedge candidates using a depth-first search. Starting from an empty set, we expand nodes step by step following the DFS order. This strategy forms the basis for our pruning scheme later. The key idea of our pruning strategy is to exploit the anti-monotone property of the scoring function. Once a candidate's score falls below the threshold, any superset of the candidate cannot exceed the threshold either. For example, if the score of candidate AB is below the threshold, we can prune all supersets of AB from the search space. This allows us to safely prune not only the candidate itself, but also its entire subtree, significantly reducing the search space. Unfortunately, however, our scoring function is not anti-monotone, so we cannot directly prune candidates using a threshold. To address this, we construct an anti-monotone upper bound of the scoring function. This allows us prune candidates and their supersets when their upper bound falls below the threshold. The score of a hyperedge candidate can increase when additional nodes are added. For example, even if ABC is a superset of AB, each score can be higher than that of AB. Because of this property, our scoring function is not anti-monotone, so we cannot safely prune supersets based on the score of their subsets. This motivates the need for an anti-monotone upper bound. We define an anti-monotone upper bound that is always greater than or equal to the actual score. If the upper bound of a candidate falls below the threshold, none of its supersets can exceed the threshold either. For example, if the upper bound of AB is below the threshold, all supersets such as AB, ABC, and ABD can be pruned. This technique allows us to significantly reduce the search space. If the upper bound of a candidate is above the threshold, we continue expanding its supersets in the next search step. For example, if the upper bound of AC is higher than the threshold, each superset ACD is also explored in the next stage. In the final step, we evaluate the scores of the candidates that pass pruning and select the top K hyperedges with the highest scores. We conducted experiments on 10 real-world hypergraph datasets across 5 domains. The hyperedges in last 3 domains are time-stamped, which allows us to incorporate temporal information in scoring. Here are the experimental settings. We split each dataset into 80% observed and 20% new hyperedges. For datasets with timestamps, we split based on time, and for others, we used 5 random splits and averaged the results. We measured accuracy using recall, which counts how many of the new hyperedges were correctly predicted. The number of predicted candidates was set to 1 times, 2 times, and 5 times the number of true hyperedges. We compared HyperSearch against 2 baseline settings, a single-stage baseline and 2-stage baseline. In the single-stage setting, we used CNS, which randomly replaces a node in a hyperedge to generate new candidates, and HPRA, which predicts new hyperedges using resource allocation. In the 2-stage setting, the candidates from CNS and HPRA were further refined using hypergraph neural networks. Here, we present the results under non-temporal hypergraph settings. Each entry reports the average recall with its standard deviation, and the best scores are highlighted in green. The bottom 8 rows correspond to 2-stage baselines refined by HNNs. The results clearly demonstrate that HyperSearch consistently outperforms all baselines across all datasets and all prediction settings. Now, let's move on to the temporal hypergraph results. Since AHP requires node features for training, it is not applicable in this setting. We can observe that HyperEdge achieves the best performance across most experimental settings. Next, we take a closer look at case studies of HyperSearch's top scoring predictions. The predicted HyperEdges capture semantically coherent combinations of texts, showing that the predictions align well with meaningful concepts. For example, in the math domain, the predictions include closely related texts such as calculus and integration. Similarly, in Ubuntu, the predicted combinations involve coherent system-related texts. Let's turn to the runtime comparison between HyperSearch and baseline methods. HyperSearch runs faster than deep learning-based methods in most cases, demonstrating its computational efficiency across diverse datasets. Here, we examine how the runtime of HyperSearch scales with the number of hyperedges. The runtime grows almost linearly, indicating that HyperSearch maintains scalability as the data size increases. Finally, we analyzed the ablation study of HyperSearch. We compared HyperSearch with each variant where each component, relaxation, and time weight was removed. Across all datasets, HyperSearch achieves better or at least equal performance, confirming that both components play an important role in improving accuracy. To wrap up, this work tackles HyperEdge prediction in a vast search space. We built HyperSearch based on key observations in real-world hypergraphs, designed a scoring function to evaluate candidates, and developed an efficient search scheme. Our experiments on 10 real-world datasets demonstrated strong performance in both accuracy and efficiency. This concludes my presentation. Thank you for your attention.